All right, so we're going to start our section 5.2, chapter 5, section 2 of our study guide. So to practice for our test. So to study for our test, so I'm going to first do the vocabulary because it's quick. We should all know it. You guys should be able to say it along with me. And then we're going to do some of the problems we actually have to work out. Okay, so when 3 or more lines intersect at one point, that point of intersection is called the point of concurrency, right? Okay. So the 3 angle bisectors of a triangle intersect in one point called the incenter. I'm assuming you guys are saying that this is too easy and that that I'm wasting your time. Good. I want you to think that I'm wasting your time because then that means that the material is easy and you guys got it. Okay? The 3 perpendicular bisectors of a triangle intersect in one point called the circumcenter. So remember, guys, for circumcenter, these steps, they're all listed on your Google Classroom. So I don't want to dwell too much on it, but you have to know these things, okay? Circumcenter is very important. Okay, so your circumcenter is the center of your circle that's circumscribing your triangle. Okay, let's start from the beginning. Your circumcenter is the point of concurrency of your perpendicular bisectors. That circumcenter is equidistant to the vertices of your triangle. Why? Because there's an invisible circle circumscribing that triangle. And that circumcenter is the center of that circumscribing circle. And what points of the triangle are on that invisible circumscribing circle? The vertices. So what do we know about a point, the center of a circle, and a point on that circle? That's just called a radius, right? It's just a line segment. So, and that's what proves that from the circumcenter to the points of a triangle, they're equidistant. We're going to review that really quick before the exam, so I don't want to dwell too much on it, but I just want to let you guys know that the same way I can reiterate it off the top of my head is not because I'm smarter than anybody else. It's because I repeat and repeat and repeat, and that's how you get better at everything. You know, repetition, practice makes perfect. So please review that, review your slides, review this video, obviously, and please review whatever little pointers I give on your Google Classroom because it's very important. I do it for a reason, okay? You guys should take advantage of that, okay? So a triangle's circumcenter is outside the triangle when in an obtuse triangle. When is your circumcenter inside your triangle? When it's an acute triangle. When is it on your triangle? When it's a right triangle. Now, where specifically is your circumcenter in a right triangle? Everybody usually says the hypotenuse, and that's true, it is, but even more detailed, where exactly in your hypotenuse is your circumcenter? On the midpoint of your hypotenuse, okay? Okay, so a triangle circumcenter is on the triangle on a right triangle. Okay, very important, okay? Can be inside, on, or outside the triangle. So I know circumcenter for sure. What about both? Can an incenter be inside your triangle? Yeah, right? Because your incenter has an inscribed circle. And the center of that inscribed circle is called your incenter. How can that center, that incenter, ever be outside the triangle if it's the center of an inscribed circle? It's impossible. So the only time for now that your point of concurrency can be inside and on and outside your triangle is your circumcenter. We know in 5.3 there's one more, but I don't want to get into that right now. Let's just focus on 5.2, circumcenter, okay? Okay. That's weird. Okay. Sorry, guys. I don't know what's going on with this right now. Okay. A point of concurrency of a triangle. A point of concurrency is just a circumcenter or an incenter. So, yeah, it's both. A point of concurrency of a triangle. You can have a point of concurrency called your circumcenter and a point of concurrency called your incenter. So that I didn't really, okay, I don't know what is going on there. So let's just, I assume you guys trust me to put the right answer. The point of concurrency of the angle bisectors is the incenter, right? We know that for circumcenter, your point of concurrency is not where the angle bisectors intersect. Your circumcenter is where the perpendicular bisectors intersect. Your point of concurrency of angle bisectors is your incenter, okay? Now, the center of the circle that passes through the vertices of a triangle, well, we know that the center of our circle that passes through the vertices of the triangle isn't that just your circumcenter? Because what do we know about a circumcenter? A circumcenter is equidistant to the vertices of the triangle. So they're obviously going to pass through it, right? So that's our circumcenter. Remember that our incenter is equidistant to the perpendicular sides of the triangle, not to the vertices, okay? All right. Center of the circle that touches each side of a triangle only once. That's your incenter, okay? All right, perfect. Now I can get out of this because I don't know what's going on over there. Okay, so now let's take a look at this question. We should all know these already, all right? So point O is the point O is the what? Well, I know that point O is an intersect. It's where a lot of lines are coming together. You have these blue dashed lines and you have these red lines. So let's take a look at let's just take a look at the triangle as a whole. What's happening to this triangle? Well, I know that it's being bisected, right? All of the sides were bisected. At what though? Obviously at a midpoint, duh, it's bisected, right? So I know that L is the midpoint, but what else do I know about OL and OJ and O and OK? What do I know about that? That's a what? A perpendicular bisector, right? Because it bisects it. This line segment OL bisects this line segment HI at a what angle? At a 90-degree angle. So that's a perpendicular bisector. And what do we know about a perpendicular bisector? And another perpendicular bisector. Look, perpendicular bisector, another one. Perpendicular bisector. We know that they all intersect at a what? Circumcenter, right? Circumcenter, okay? And we know that a circumcenter is equidistant to the what? To the vertices of my triangle. So the only thing I know is that OI is congruent to OH is congruent to OG. Now, I know I've said this analogy in class, but it bears repeating that your perpendicular bisector measurements, this 5, is just there to trick you. This 5, I don't care if this was 5 or 15 or 20 or 100. I don't care. Your perpendicular bisectors are kind of like your Uber drivers. You don't care how long they took to get there, right? I don't care that this guy started at L and had to drive all the way over here while this guy only had to go only this distance. We don't care. The only thing we care is the destination where they dropped us off, which was where? At the circumcenter. So this 5, if this was 5 also and this was 7, it does not matter. Okay, the only thing I care about is the circumcenter to the vertices of a triangle because I know they're all equidistant. So if OI is 29, what do you think OG is going to be? 29. What do you think OH is going to be? 29. Okay, so now let's look back. So this was all things that I've gathered, not even looking at my question. I'm just looking at the triangle, okay? So now point O is the what? Circumcenter. And OG, I'm looking here because I can't click on this. This is my Good Notes app so I can write and stuff. My OG is what? My OG is a line segment starting from the circumcenter to the vertices to the vertex of the triangle. So I know it's a what? It's it's equidistant to OI. So this is 29. Right? So my answer will be 29 over here. Okay, so let's take a look at this one. Now, I'm looking at my triangle. Oh my God, look at this. Look at this, guys. Look, another perpendicular bisector, right? Because perpendicular, wait, what? What happened here? There's no indication that any bisection took place. There's no tick marks. So Is this truly a perpendicular bisector? No, I don't have perpendicular bisectors. So now I need to take a look at what else I have. So there's a perpendicular segment, yeah, sure, but that I don't know nothing about any point of concurrency with perpendicular segments. But what do I notice? I have one arc, 3 arc, 3 arc, 2 arc, 2 arc. So what do I know that's happening to these vertices of the triangle? These vertices of the triangle are being bisected by what? Angle bisectors. So if I have angle bisectors, I know that my point of concurrency of angle bisectors is a what? Is an incenter. And what do I know about incenters? My incenter is equidistant to the perpendicular sides of the triangle. So I know if PB is 6, what do I know about PC? It's also 6. What do I know about AP? It's also 6. Once again, guys, I do not care about the length of my angle bisectors, about my FP and my EP and my DP. I don't care about none of that. I only, once again, your perpendicular bisectors and your angle bisectors, think of them as your Uber driver, as an Uber driver. I don't care how far it took him to get here. I only care about where he left me off. And where did he drop me off? At the incenter. Okay, so now let's look at the question. Point P is the incenter. PA, well, I know if PB is 6 and PC is 6. What is PA? If BP and PC and PA are all equidistant, then I know that PA also has to be 6. So my answer is 6. Okay. Now, this one. Find the coordinates of the circumcenter ABC. So I'm going to draw, look how fast I'm going to draw this. It does not have to be fancy. A, remember guys, always draw your things out. -6, 0. -6, -3. So what type of triangle do I have here? I have a right triangle. How do I know that? Because I have a horizontal line at y equals 0, correct? And I have a vertical line at what? X equals -6. And what do I know about a horizontal line and a vertical line? They converge at a 90 degree. So I have a right triangle. Now, I know that my circumcenter is going to be the what? What is my circumcenter of a right triangle? It is the midpoint of the hypotenuse. Now, please do not say your hypotenuse is the longest side of a triangle. That is not true. Your hypotenuse is the side opposite to the 90 degree. Okay? So, I could just find my midpoint here, but what if we wanted to do it the old-fashioned way? Mister, what's the real way to do it? I don't want no tricks, right? I'm sure somebody might say that. So the way you got to do it is you got to find your what? What do we know about a circumcenter? How do you find your circumcenter? Isn't your circumcenter the point of intersection of perpendicular bisectors? So I need to perpendicularly bisect at least two sides. So let's say I want to bisect this one perpendicularly. What is the midpoint? I know that if I'm going to bisect something, where is it going to cross through? The midpoint. Whoa. Okay, I know that it's going to cross through the midpoint. So what is the midpoint of -6, -3, and -6, 0? That's just going to be -6, -1.5. So -6 and -1.5. Cool. Now, I know that this is, what type of line is this? It's a vertical line. What do I have to do? What type of line do I have to intersect this line in order to get a 90 degree? It's just a horizontal line, right? So what do we know about horizontal line? What is the equation of a horizontal line? Horizontal lines are y equals c, and vertical lines are x equals c. So if I draw a vertical line right here, right? What is a horizontal line? It's what? It's y equals c. So if our horizontal line is y equals c, well, what is the y value of this coordinate right here? -1.5. So I'm going to have -1.5. Okay? So now let's take a look at this right here. Well, this is a horizontal line, right? So I want to find the perpendicular bisector of this line. So where's my midpoint at? because that's the point that I need to cross in order to get my perpendicular bisector, right? So this is going to be -3, 0. Okay, and what type of line must I draw intersecting this midpoint to get a perpendicular? A horizontal line. I mean a vertical line. I apologize. A vertical line. And what is the equation of a vertical line? It's x equals c. So what is the x here? -3. So that is my, because really what I have here is y equals -1.5 and x equals -3. And what do I know? If I have these two lines, what is the point of intersection of this line and this line? It's going to be this point right here. So if we wanted to do it with our proof, so that's just a quick way to, you guys, well, that's the long way to do it, right? It's going to be somewhere over here. Well, the other way to do it, the shortcut way, which is fine, I don't care. If you can recognize that you have a right triangle and you have a shorter, quicker, more efficient, less prone to mistakes type of way, then please do it. So, okay. So, what is midpoint, guys? We should all know midpoint. Midpoint is equal to x1 plus x2 divided by 2, y1 plus y2 divided by 2. What is our x in this case? My x over here, x1, y1, x2, y2. What is -6 plus 0 divided by 2? -3. What I did here, guys, is I did x1 plus x2. What is -6 plus 0? -6 divided by 2, -3. What is y1 -3 plus 0? -3. What's -3 divided by 2? -1.5. -1.5. So you see how we found our answer. Both our answers were the same, just different ways to do it. If you recognize that you have a right triangle, you can go ahead and find, and you can go ahead and apply what you know about the circumcenter of right triangles to find your circumcenter. If you don't, this is the way that it'll work for every single situation. You pick two lines, okay? And then you find where they have perpendicular bisectors at, and where those perpendicular bisectors intersect the line segments or the sides of the triangle, and where they're going to intersect each other. And that point is right here, your circumcenter. Okay? So, this is another tricky one, I feel like. So, name the point of concurrency of the angle bisector. Okay, so I know I'm going to have a midpoint, right? Not a midpoint, an incenter, right? Point of concurrency of angle bisectors. That's going to yield me an incenter. So, let's take a look at my angle bisectors. Where are my angle bisectors? I have this guy right here. So, I'm going to go ahead and draw it in blue. So, I have this right here. Wait. Oh no. Hold up. My bad, guys. Okay. I know there's a way to like... Oh, here it is. I'm so silly. Okay, yeah, right there. So now... Where was my... Okay, what's going on? Okay. So I'm going to erase this because it's like covering up everything. Okay. So I'm going to have CZ right here, right? And now what's my other angle bisector? I have this guy right here. And I also have this angle bisector right here. So where did all of these three angle bisectors converge at? Their point of concurrency? B. And that's it. My answer is just B. Okay? So now, once again, find the value of x. Okay, well, before I find the value of x, I have to see what I'm even looking at. I'm looking at a perpendicular bisector. No, not perpendicular bisector, right? I'm looking at perpendicular segments, okay? So that kind of clues me in that maybe I'm dealing with an incenter problem. So let's see, do I have angle bisectors? I don't have any angle bisector here, but I have here and here, perfect. So I know I'm dealing with an incenter. So I know that this point has to be my incenter. And what do I know about the properties of incenter? The incenter has the incenter is equidistant to what? To the perpendicular sides of a triangle. So now I know that this and this value and this value have to be equal to each other. So 5x minus 3 is equal to 8x minus 12. I'm gonna subtract the 5x here, subtract 5x there, add 12, add 12. So I'm gonna have 3x equals what, 9? So my x is 3. There you go. And that's it, guys. It's not hard. I think we've done this a few times enough already. So let's take a look at this tricky question. You're trying to talk to a friend on the phone in a busy bus station. The buses are so loud that you can hardly hear. Referring to the figure to the right, should you stand at P or C to be as far away from all the buses? This is the key. This is the key word right here. All the buses. Okay? So if I were to stand at C, I'm super far from these buses, right? Super far from those buses. But I'm pretty close to this one and like decently close to this one. So would I want to stand here? Probably not, because I'm way too close here. So where would I want to stand? Maybe I want to stand at P, because I feel like this distance is pretty good. This distance looks pretty good. And man, this distance also looks pretty good. They all pretty much look like they have an equal distance away. But how do I know that? What am I going to look at? Scaling? I'm just going to rely that this is drawn to scale? No. I'm going to see what I know about circumcenter. About circumcenter and incenters. Well, what do I know about circumcenter? Circumcenters is the intersection of perpendicular bisectors. Do I have any perpendicular bisectors? Yeah. Right here, I have this, perpendicular bisector. Perfect. Oh, look, I have another perpendicular bisector. So I know this C is my circumcenter, stands for circumcenter. I guess that's why they did it. And now let's look at this P. I have angle bisectors. So now I have angle bisectors intersecting at this P. And what is this P going to be? Incenter. Now, let's go back to circumcenter. What do I know about circumcenter? If I want to be as far as possible from all the buses, that means I want to be an equal distance away from all the buses, correct? Well, where do I know? Where are the buses? Are they on the vertices of my triangle or on the sides of my triangle? They're on the sides, guys. So if the buses are on the sides of the triangle, I'm gonna want to find a spot where I'm gonna be as equally away from the sides as possible. And which gives me that answer? What allows me to be as equally distant from all the sides of the triangle? My incenter. So my answer is incenter. Okay. P, which is the incenter, because it's equidistant from the sides. Okay. Everybody got this question pretty well last time, so I think we'll be fine. So let's take a look at this one. This one was kind of tricky for some people. So in the diagram, which is not drawn to scale, G is the incenter of DEF. So I know if G is the incenter, so if I know that G is the incenter, what else do I know, guys? Whoops. If G is the incenter, what else do I know? I know that to have an incenter, I need to have what? Angle bisectors. So I know that this is looks like that. Like that. Do you see I'm already like implementing things that they're not even telling me, because what if it comes in handy? It took me like 5 seconds. So G is the incenter of DEF, and EFD, where's EFD? So this whole angle was how much? 50. This whole angle, EFD. So even though this angle EFD is being bisected, I know that the whole EFD is 50. Okay, cool. Now, find the measure of EFG. So where's EFG? This one. So I know that EFG is the measure that I actually want. Well, what do I know about the whole measurement right here? What do I know about that entire measurement? Well, the whole thing is 50. So if the whole thing is 50, and I know that EFD was bisected, well, if it's bisected, wouldn't EFG be one of those bisected parts? And wouldn't GFD be the other one? And I know that they're congruent. So what does this one have to be? Just divide by 2 to find it, right? Because if this whole angle, this 50, is being bisected, I know a bisection is being divided in half. So my answer is 25. So now this one looks very similar, but it's a little bit different. So let's take a look. In the diagram, which is not drawn on scale, G is the incenter. Okay, cool. Wow. So far, it's actually the same, right? So this is the incenter. So this is the incenter. What else do I know? I know that I have this, 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 and this, right? Okay, cool. So now, G is the incenter, okay? EDF is 54. EDF is 54. Okay, so this whole thing right here, this whole angle is 54 degrees. Okay, EDF. Okay. Now, measure of DEF is equal to 2 times EFD. Okay, so now it's a little bit tricky, right? Because now we have 2 unknowns, and one of them relies on the other. So whenever you guys want to solve for 2 things, especially angles like this, you always want to put the smaller one. Well, what you're going to do is, what do you know if you have a value, right? But if you have a term, right? You see how this is a term and this is a term, but you don't have a value for it. You don't have a numerical value like let's say this is 54. It's not. I'm just saying a value like this. You need to put a variable. It can be X, Y, A. It can be a smiley face for all I care. It doesn't matter as long as it's a variable, right? So let's say X. So I'm telling you, if you want to put your smallest value, you want to give your smallest value the actual variable. Why? Because now from here to here, we're going to be multiplying something. That's a lot easier than going from here to here, which we're going to have to, what's the opposite of division? Multiplication? Division. So let's first find this measurement right here, EFD. So EFD, let's take a look. EFD, okay. So let's say that I want to give my measure of EFD. EFD, let's say I want to give it a value of X. Well, if I give my EFD a value of X, why is that kind of tricky? Why is that gonna trip me up in the long run? Because what is happening to this EFD, guys? What is happening to this EFD? It's being bisected. So that means if I'm gonna have to bisect this entire thing to find my individual angles of EFG and DFG, what do I know about these 2 angles? It's gonna be bisected, right? So it's gonna be half of X. So do you guys really want to work with 1/2 X and 1/2 X? I don't want to do that. I don't like that. That's not fun, right? So what other variable do you think that I can assign to EFD to make my life a little bit easier when I get that bisection? You're going to want to put 2X. Because let's see what happens when I give this whole thing a value of 2X. If this whole EFD has a value of 2X, what is 2X divided by 2? It's just X. So now I get to work with a lot easier, smaller numbers, right? So now I get to put X and X. And that's a lot easier than 1/2 X, right? Okay. So now, if I have a value, quotation marks, of EFD, at least I have something, right? I have something to go off of. I have some sort of numerical inkling, right? I have a variable, right? So now, let's actually find out what is the value now, or the numerical value, or the variable of DEF. Well, if DEF, measure of DEF is 2 times this EFD. What is the value of EFD? We just decided is 2x. You guys decide what variables you want to put. You could have put 100. You could have put 100x and then each was 50-50. You just, that's silly. I wouldn't do that, but you can if you wanted to, right? You're gonna make your life complicated, but you can. We decide how we view these questions. We decide what variables we put. So if we want to go along with this is 2x, well guys, what is 2 times 2x? What is that? It's just what? 4x, right? So that means this DEF now has a value of what? 4x. So if DEF has a value of 4x, what do I know about this DEF? What do I know about this whole DEF? It's also being what, guys? It's being bisected too, because this is an intercenter, it's an incenter, so I have an angle bisector. So if I know that this whole angle is 4x, what do I know about this little piece, and this piece? They're each going to be 2x, 2x. Okay? So now I have every single nook and cranny of an angle. And look, if we even wanted to get really, really specific, we can say this is 27 and 27, right? Because it was bisected too. So let's see if that's going to help. I'm just doing everything I can so that when I actually read what I still have not read what they actually want me to find. But now look how much more like filled out this triangle is. I know everything about this triangle, right? At least about the angles, right? So now let's see what they actually want me to find, and we'll find the final answer in purple. Find DFG. Where is measure of angle DFG? DFG. What is the value of DFG, guys? What is the value of DFG? It's just one little x right here. Just that one x right here. So now how do I solve for x? I need to use my triangle angle sum theorem to find out all my measures equal to 180. And then I'm going to solve for what? Solve for x. So let's do 27 plus 27 plus 2x plus 2x plus x plus x equals 180. So I have 2, 4, 5, 6, 6x. What's 27 plus 27? We already did it right here. It's 54 plus 54 equals 180. What is 180 minus 54? 10, 7. I don't have my phone on me right now, so I can't use a calculator. All right, divided by 6, which is going to be 21. So my x is 21. So if I have my value of my x, what is the value of my DFG again? What was the value of my DFG again? It was just x. So that's it. So my value of DFG is 21. Okay? I know that's tricky, guys, but it's only tricky because of the setup. Once the setup is complete, it's everything we've done these whole couple weeks, right? And now last one, find the value of x. Well, I already know, we should already know that this is perpendicular, so this is a perpendicular bisector of angle of line segment AC. And what do I know about any point that is, what do I know about a point on a perpendicular bisector and its relevance to the endpoints of the line segment? That they're equidistant. So I'm just going to do 25 equals 4x minus 3. 28 equals 4x. So x is what? 8, right? No. 6, 12, 18, 24, 7. 7, 14, 20, 28. That's it. So x is 7.